Hello everyone, today we're going to do problem 12.35 from Fundamentals of Heat and Mass Transfer by Bergman and Levine. The problem is written as follows. It says a small metal object initially at Ti is equal to 1000 Kelvin is cooled by radiation in a low temperature vacuum chamber. One of two thin coatings can be applied to the object so that the spectral hemispherical emissivities vary with wavelength as shown. For which coating will the object most rapidly reach a temperature of TF or T final of 500K? And we're given this chart here that shows that coating A initially starts with a high emissivity, and then after 10 microns of wavelength, it drops to about 0.25. And then coating B is actually the opposite, where it'll start low, then jump back up. So what we're given is we're given the initial temperature at 1000 degrees Kelvin, and we're also given the emissivity as a function of the wavelength. And what we're asked to find is for which coating will the object most rapidly reach a temperature of 500 Kelvin. So our schematic is roughly going to look like this. We have our object here in black. We can apply either coating A or coating B, and we're assuming a spectral hemispherical emissivity from each coating. And some assumptions we're going to make. We're going to assume that the object is opaque and diffuse, so there's no transmission. And we're also going to assume that there's only radiation heat loss, since we are told that it's in a low temperature vacuum environment. So for coating A, we can start by looking at the integrals for the emissivity. And we'll start with this full integration, and then we can divide that and use integration by parts to essentially look at the integral from 0 to 10 micron, and then from 10 to 100 micron. We could also write this using the black body assumption and say that E, the emissivity, is equal to epsilon 1 times this F value from 0 to 10, which we'll get from table 12.2, and then emissivity 2 times the F value from 0 to 100 micron minus the F value from 0 to 10 micron. And if we go ahead and go to table 12.2, we can actually calculate these two values. So from lambda 1, so from 0 to 10, we'll multiply that by our given initial temperature of 1000 degrees Kelvin. We can see that we have about 10,000 micron per degrees Kelvin. And when we go to our table, we'll find that gives us an F from 0 to 10 micron equal to about 0.914199. Same thing from 0 to 100. We can plug in the 100 here for our wavelength, and we'll get a value of 0.999905. We can now use both of these and plug this into our previous equation and find that we'll get a total emissivity value of about 0.7071. And if we do the same thing for coating B, again, we'll take our integral, we'll use our black body assumption, we'll get our values from our table, which are going to be the same, since we're again multiplying 10 by 1000 and 100 by 1000. And then when we plug in our emissivity, so in this case, we're going to go from the low emissivity of 0.25 to the high emissivity of 0.75. We're actually going to get a much lower number for the emissivity of 0.2928. And so we can go ahead and compare these two by calculating the total emissive power from each. And we'll do that by just using our simple equation up here of epsilon, or our emissivity that we calculated, times sigma, the Stefan-Boltzmann constant, times T to the fourth. And we'll use our initial temperature. And we can see for coating A, we're actually going to get a total emissive power of about 40 kilowatts. And for coating B, this should actually say B for our secondary coating, we're only going to get a dissipation of about 16 kilowatts. And so we can clearly see from this value that coating A will cool the object much faster than coating B. And we could also skip the math and kind of make some assumptions about this by looking at the emissive power of a black body. And if we look at this chart with the emissive power as a function of the wavelength, and we find our 1000 degree Kelvin line, we're really looking for the area under the curve as our total emissive power. And we can see that from 0 to 10, we have kind of our peak of our curve here. And then from 10 to 100, we start dipping off. So if we assume the area under the curves there, we can see that there's a lot more power dissipated from 0 to 10 microns of wavelength than from 10 to 100 microns of wavelength.